Good morning, everyone. So, my name is Chani Dinita, and today I am going to present my final year research project called HalloScan. So, this project is about detecting hallucination in large language models by looking at their internal hidden status. So, I will walk you through the problem gaps I found in the existing research and how I built the system and the result I got and also the limitation. So first I will go with the problem part. So what is the problem? So in large language models like GPT, Claude, Llama are now used everywhere, right? In education, healthcare, custom service, researchers, everything. So they are very powerful, but they have serious issues. Sometimes they give answers that sound perfectly correct but are actually wrong, so that is what we called as a hallucination. So there are two main type of hallucination: factual hallucination and faithfulness hallucination. So factual one is it's like when the model says something that contradict real world facts, something like that. And the faithfulness one is when the model goes against what the user asked or contradict what it already said, something like that. So that's what in the hallucination problem means. So in here, problem definition and the motivation. So let me explain the specific problem I am trying to solve. So the main problem statement is this: the current hallucination detection system check answers only after the full answer is already generated, and they mark the whole response, it means whole answer, as wrong even only small part, like small sentence part is wrong. This make them slow, expensive, and not practical for a real time use. So I found three main limitations in the existing system. So first, they are like post hoc only. The wake after the answer is done, not during the generation. And the second one is coarse granularity. They flag their answers instead of pointing to the exact wrong part. And the third one is ignore the hidden states. It means which already contain signals about when the model is uncertain. So then we will go with the research gaps. So now let me talk about the research gaps I found from reviewing the reviewing the literature. So first gap is like this is the first gap: fine gained localization. Most existing method give a single yes or no verdict for the whole answer, but in reality a hallucination might only be in the one sentence out of five. So we need sentence level detection where each sentence is checked individually. So that's the main gap. And then second gap is about hidden status. The model actually knows a lot of things internally, but sometimes it still outputs the wrong thing. uh, Therefore, like researchers have said, we need to study this internal state more deeply. So like reading them during the generation, not after that. Likewise, so the third one is the about like uncertainty. Just because a model is consistent or show low uncertainty does not mean it is the correct one. It can repeat the same wrong answer with high confidence. So we need better ways to connect uncertainty to actual truth part. So that's are the gaps we have. So then we are go with the literature review part. It means the existing approaches. So in my literature review, I studies four main categories of existing approaches. So first is the external fact checking. So in here you compare the model's output against trusted sources like Wikipedia or something like that. Then it is accurate but very slow and expensive. So and it depend on having a good external database also. So then second one is the uncertainty estimation. So you look at the model's own confidence scores. It's like self-check GPT is a good example for this. It generate multiple answers and check if they are consistent, but the problem is model can be confidently wrong. That's the case, so giving the same wrong answer every time. Then we have the internal state analysis. So which is what my research focus on. Methods like the signals like the TSV, it means like truthfulness, separator vector, then distribution, halo shift. So look at the model's hidden layer to find signals of the hallucination, but they need white box access. So they do not work with closed models like ChatGPT. So then we have the supervised detection, where you train the classifier on label data. It can be accurate, but the label are expensive to create the classifier not generalize well. So that's what we are like talking about. So these are the like existing approaches they that I have for the hallucination detection. So then I will go with the my benchmarking part. So in benchmarking, so what we have existing methods. So let me show you how these existing methods compare. So we have the gray box methods like average, negative, log probability, average, probability achieved about 83%. Yeah, AU AOC PR on the self-check GPT Wikibio dataset. So, but they need token level probabilities, which most commercial API do not provide, something like that. So then we have the black box methods like self-check GPT with the Briscoe got like 72%. They work without seeing the model internals, but they need multiple samples, which is slow one. So then they have the search argument method like fact score, like verify each fact against the knowledge base. They are uh, it like they are thought but expensive and slow. That's why. Then we have the internal state methods like TSV, Agenisco, show like they are show a strong result on the truth QA, but they use only a one signal and work at the whole answer level. So that's what that is the issue, because like they are using a one signal only. So the key takeaway is no existing method combine like multiple internal signals with the sentence level detection in like a one pass, because there are many things happen. There are many methods they have. We are like using the one signal then detect as, but there are no anything like they are getting creating more than like more than getting more signals and creating something like that. So then I will go with the seventh slide. So this is research aim and the question. So here is my research aim. I wanted to design and evaluate a white box sentence level hallucination detection framework that read the LLM's internal hidden state in a single pass and fuse three singles into one reliability weight score. So I had four research questions. So these are these research questions. So how can hallucination be detected from the hidden status in single pass? Then second one was how can we localize them to a specific sentence? Third one was does combining multiple signals actually help? And fourth one is can it be fast and accurate enough for the practical use? So that's I have the for research questions with my idea. So then I'm go with the hello scan, it means my system architecture part. So now let me explain how a hello scan works. The pipeline is unique, simple one, and first thing was user ask a question, then LLM generate an answer. During the generation, I extract the hidden state from the middle and the later layer. So these hidden states go into the tree. That's we are getting tree, like we are getting hidden states. No, then like that hidden state is go into three detectors: SCP and HelloShift and the TSV. So their scores are then combined using the learned fusion model, so which is basically logistic regression classifier. So then the system break the answer into sentence, okay, then filter out non-fact part, greeting or filter, and score each factual sentence individually. That's what happening. So finally, the risk sentence are highlight in the web inference: reliable or uncertain or likely hallucinate one, likewise. So three key design decision. First, I use single shared model for the all three detectors. There is only one forward pass. So second, I use the NLI basic claim filter to remove non-factual sentence also. And third, I everything happens at the sentence level, so user can see exactly which part is risky. So sentence by sentence they are giving the risky part. So then um, I will go with the three internal state detectors. So let me explain three detectors. SCP first stand for a semantic entropy probing. It trains a lightweight probe on the hidden state to estimate how uncertain the model is internally. On the 8 billion model, I got an 0.77 around amount. So then we have the hello shift that will represent the distribution shift. So it track how feature distribution change across different layer using the measures like versus change distance. And if there is an unusual shift, it might mean the hallucination. And I got like 0.8 mount AUR for the AURC. So that was a one good one. And then we have the TSV. So in the TSV, truthful separator vector, so it learn direction in the latent space that separate truthful outputs from the hallucinated one. So individually it got 0.759. So but we have combined all three together, and that is where the real power comes. So then I will go with the evaluation result part. So now these are the results. So almost important number is the a 0.833. That is the first AUROC on the 8 billion model in the domain test set. So the fusion of all three detectors outperforms every single detector individually. The best single detector was HelloShift at 0.800. So the fusion generally added value to that also. So one smaller model like 1 billion model fused AUROC was 0.765. So detecting quality improve without model size. The large models hidden state giving clear signals. That's their properly working. For the cross data sets, the best was 0.751 on the squad. So train on trivia QA. So some key find the no singles detector is based on every data set. So the fusion provide stability. That's the important part also. And next we have the cross data set benchmarking. So This slide show how the system perform on the data set which never trained on. So the model was trained on Trivia QA and tested on Squad, Pop QA and PsyQ without any retraining. So what we see is that no single detector is consistently the best. On Squad, SCP does well. On PopQA, TSV is the best. But the Fusion is a reliable competing across all dataset. That is the important part in my case. So it will never collapse like a worst detector, but it will go with the very clear number everything for the everywhere. So I also compared logistic fusion versus rank means fusion. So I the rank means fusion transfer mode safely across dataset. So that is what the final system uses. So that's what happening here. And then I will go with the expert evaluation and strength. So the system was evaluated by domain experts and technical experts also. They confirm all the key it means like key criteria is okay. Detection during generation works. Hidden state single produce meaningful score, and the sentence level highlighting is also working. The fusion is just justified because it beats single detect also. Then we have the behavior on the factual claims. It means like for a one word something like that. So that was like a partially thing. So now yeah, on the strength side, the ablationist study honestly showed the which detector helped for them and likewise. So then we are go with the limitation and the threats to validity. Now let me honest about the limitation part. So moderate generalization. It means on unseen data, AUROC dropped the 0.60 to 0.75 compared to 8. It means like 0.833 in domain. So the system is best used as the warning tool, not a perfect detector, something like that. So then length style confused. Sometimes the detector are influenced by how long the answer is, not just whether it is true. So I mitigate this by moving to sentence level scoring, but it is still a limitation. So this is for the white box only. The system need as the model's hidden states. That's the case. So a small noisy test set. So around like 100 to 150 something like. No sentence level ground truth. There are no human label for the individual sentence. So localization is only evaluated immediately. So then we have the limited model task scope. So only test on QA task with two llama models. Other tasks will be evaluated. So then I will go with the future work part. So in the future work, first test large and more varied like model. I want you to see how the hidden state single scalar with the bigger model also. And then second, collect human verified sentence label. Right now there are no human annotation for the individual sentence, so I wanted to create a proper data set for that. That's the second one. And the third one is at true token level detection. I prototyped the token level highlighting but could not include it the final year system because like the hours go through at the level. So then we have the final fourth one, exploring adaptive fusion weight that adjusts based on the question type or a domain. And then yeah, thank you. To conclude, the hallucination is like a white box sentence level hallucination detection system based on internal hidden state. So and yeah. Yeah, and finally, like it combined three detectors through the learn fusion model and the HO like 0.83. So that's the basic idea of this thing. And now I will move into the my coding part. Yeah, so in here you can see this is how my UI looks like. So in here at the top we have the status dot and backend address and llama to llama models, and then we have the highlight on and off, and we have some information about how these scores are working, something like that, and we have then clear history. So first I will what we called go with the 8 billion llama and then clear the history. So put OK. Now it's look like this. So first I will put some questions. There are here some questions. Who is the who painted the Mona Lisa? So it's like a simple true fact question. So yeah, then LLM generate the correct answer. Leonardo da Vinci painted the Mona Lisa. So they will printed the risk amount, and then uh, the graph also put it in green color, and then we are going with the tricky question with the false permission. Who was the lead architect of the Eiffel Tower 1950 expansion? That should be hallucinated one, because like there was no 1955 expansion of the Eiffel Tower, so that's the case. So it should be the hallucinated one. So it will generating. Mm, 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 mm. And here you can see like in my system they are getting like for a sentence they're giving okay, my first one is this percentage, and STP hello shift TSV is something like this. So they are they are giving okay, now we got the answer. So yeah, that is a wrong answer. Then model, what happened, model was confused what, because there was no 1950 expansion, no, therefore model was get confused. Then they will like printing same thing again and again, but the answer is wrong. Then they will tell okay, each and every answer is wrong. Then they will highlight each and every answer and then tell okay, this is the hallucinated one. And you can see in the graph for the first question how it's look like, and then second question how it's look like. And you can see in first question, when I go with this question, you can see the amount was very low. In the fused one TSV, same for the fused also, like they are getting more numbers, right? In here, in the red color one, they are getting like more high amount. It means like it was a hallucinated one. That's the case. So then we are try with the long answer, true long answer. True long answer. Okay, give me 5 facts about India. Mm, okay, it is still running. And next you have to put to like what we called. Hmm. Okay, I got the answer. So that's a correct answer. So therefore they will got like a green color. So that's what happening here. You can see for the reaction how it looks like for the graph and the this box also. Mm, yeah, so that's basically what's happening here. So then I will go with the coding part. mm, 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 mm. So basically in simple way, how this is working properly. So how this is working properly. So first thing was, like, my page sent the question to the API server. It means in here there is a front end, src and app.js. This is the file that's where happened. And then they are like, server take that runs to choosing the model. They go with the backend and app.py and then run it. Okay, then we choose the answer to the sentence. It means like, then after that AI write its answer using the what we call the Hallukin engine. Under the Hallukin engine, this thing, in here, like, AI write its answer. Then each sentence get the score, right? After they write the answer, they will get the score. And then that will happen in the this fusion part by three detector, then judge merge them into one number. So the detector file plus Halkin version file. So okay, the number becomes a color. That's happening in the Halkin risk py part. So then important part is how my calculation is happening. So in the SCP we have like SCP adapter in here, this one. So how sure was the AI deep down, and is the AI finishes the sentence, we take the snapshot of the it state of mind, and the model trailed check the reads, and it and if the AI is secretly unsure inside that, usually means it's guessing. So score goes up. So that's what happening. And then we have the again HelloShift adapt. Yeah. Then we have the TSV also. So does this learn true or made up, something like that? So that's what happening in the TSP adapter part. So yeah. So and then again color part is happening in the risk one, and then we have the fully pipeline. So in here we are running fully pipeline. So getting answer from the user, AI answer one fact per the sentence, and three detector check the each sentence, and judge merge them into one trust score, and the score become green, yellow, or red, and the worst sentence decide on overall judge. So that is scan. So yeah, that's what we I wanted to tell. So thank you.